Welcome back to the deep dive. So today we are putting aside the buzzwords.
Things like synergy and digital transformation.
Exactly those. And we are getting our hands dirty with the actual, the plumbing of the cloud.
And it's not boring plumbing.
No, not at all. I'm talking about the digital nervous system that keeps your applications alive. I mean, if this system fails, it doesn't matter how fast your servers are. They're just expensive bricks.
They really are. It's the foundation of everything. You can have the most sophisticated AI, the fastest database, but if the network isn't architected correctly, nothing talks to anything.
Or worse.
Or worse, everything talks to everyone, including the bad guys. It's all about control.
Precisely. And to help us get a grip on this, we pulled together a pretty serious stack of sources. We're looking at the official Azure Administrator guides, some very specific in-the-trenches walkthroughs, and we're also leaning pretty heavily on the exam prep to the AZ-104.
Which is great because the exam prep, it usually highlights the exact places where things break.
That's our mission today. We want to decode how to build a private space in the public cloud, how to connect those spaces, and the big one, how to lock them all down. Because the default settings aren't always what you need.
Rarely, actually. Yeah, we need to move from plug and pray to intentional design.
So let's start at ground zero. I'm a business. I log into the Azure portal. I spin up a virtual machine. It needs a home. And that home is a VNet. For the person who just pictures, a bundle of Ethernet cables, what is a VNet in the cloud context?
Okay, so think of the public cloud like a massive open plan office building.
Okay.
Everyone is there. Your competitors, random startups, hackers, everyone. A VNet, or a virtual network, is you building a soundproof, bulletproof glass room right in the middle of that floor.
So it's my own space.
It is a logically isolated section of the Azure cloud, and it's dedicated solely to you.
So even though we are sharing the underlying hardware with who knows who, my data is strictly fenced off.
Correct. Fully isolated. And inside that room, you are the master of physics. You define the address space, usually with CIDR notation, those blocks like 10.0.0.016, and you decide exactly how that space gets used.
You mentioned the address space. The sources, they use a pizza analogy for breaking that down.
It's a classic because it works. The VNet is the whole pizza, but you rarely deploy resources directly into the raw VNet. You have to slice it up, and those slices are your subnets.
Why slice it? Why not just throw all my servers in one big bucket and call it a day?
Well, you could, but from a security standpoint, that's a nightmare.
Yeah.
You don't want your public-facing web server sitting right next to your sensitive HR database with zero barriers between them.
Right.
By slicing the VNet into subnets, you create these internal zones, a web subnet, a database subnet, a management subnet. It lets you put different security policies on each slice.
Okay, so segmentation is key.
Got it.
Now, I want to bring up something that caught my eye in the exam prep notes. It's a math problem that seems to trip everyone up. The sources call it the case of the missing IPs.
The Azure tag.
Walk us through this.
Yeah.
In standard networking, if I create a 24 subnet, which is a pretty standard size, the math says I should have 256 IP addresses.
Right.
256 parking spots for my servers. But Azure says, no, you actually only have 251. Where did the other 5 go?
This is a hard rule in Azure, and
Oh.
it trips people up constantly. Every single subnet you create, Microsoft reserves 5 IP addresses immediately. They're just gone before you even start.
Okay, so where do they go?
They're reserved for Azure's internal plumbing. And you need to know which ones, or you'll miscalculate your capacity. So first, you lose the very first and the very last address, the 0.0 and the 0.255.
That's standard networking, right? The network address and the broadcast address.
Exactly. But then Azure takes 3 more. They take the 0.1 address for the default gateway. That's how traffic gets out of the subnet.
Okay.
Then they take 0.2 and 0.3 to map the Azure DNS services.
So 0.0, 0.1, 0.2, 0.3, and 0.255 are just dead to me.
Completely unusable for your servers.
So why does this matter so much? I mean, it's only 5 IPs. If I have 250 spots, losing 5 isn't a tragedy.
It really matters if you're designing small subnets. Sometimes people create these tiny subnets for specific little services thinking, oh, a 29 gives me 8 addresses. That's plenty for 4 servers.
But with the text.
8 minus 5 is 3. You only have space for 3 servers. And if you try to deploy a 4th, the deployment just fails. So the big takeaway is you always have to plan for n minus 5.
That is a crucial gotcha. Okay, moving on. We have the VNet. We've sliced it into subnets. Now, my servers need to talk to the world.
Yeah.
And this brings us to public versus private IPs.
This is the distinction between inside the room and shouting out the window. Private IPs are for your VMs to talk to each other. Azure handles this with DHCP automatically. Public IPs are for talking to the internet.
The sources highlight a shift here.
Yeah.
For a long time, we had basic public IPs, but now everyone is being pushed toward.
The standard SKUs, right? What's
Yeah.
the difference other than, the price? It's a massive security and reliability shift.
Yeah.
The basic SKU was a product of a simpler time. It was open to the internet by default. It was dynamic, which means the IP address could change if the machine rebooted.
Open by default sounds terrifying in 2026.
It is. The standard SKU fixes all of that. First is static. The IP you get, it stays with you. But more importantly, it is secure by default.
What does that mean in practice?
It means even if you attach a standard public IP to a server, nobody can talk to it until you explicitly go into the firewall and open a port.
So basic was an unlocked door. Standard is locked until I give you the key.
Precisely. And standard also supports availability zones, which is essential if you want your app to survive a data center outage. Basic is it's essentially being retired, so if you're building new, you go standard.
Okay, so that connects us to the internet.
Yeah.
But what about connecting to other private networks? Let's say my company buys another company. I have my VNet in New York. They have a VNet in London. We need to connect them, but we want it to be private. We don't want to go over the open internet.
This is where VNetPeering shines. It is probably one of the strongest features in the entire Azure networking stack.
So how is it different from just using, say, a site-to-site VPN?
A VPN creates an encrypted tunnel over the public internet. And it works, but it has bandwidth limits, it adds latency, and you're at the mercy of internet congestion. Peering is different. When you peer two VNets, Microsoft essentially fuses them together using their own dark fiber backbone.
So the traffic never touches the public internet.
Never. It stays on the Microsoft global network. That means that it's incredibly fast, high bandwidth, and very, very secure. And you can do this globally. Your New York VNet and your London VNet can behave as if they're in the same building.
That sounds seamless. But looking at the technical notes, there's a constraint here regarding transitive traffic. This seems to confuse people.
Yes, this is the friend of a friend problem. Peering is non-transitive.
Walk us through that.
Imagine you have three networks, A, B, and C. You peer A to B, and you peer B to C. Logic suggests that A should be able to talk to C, right? Since they're all connected in a line.
Right, it should flow through the middle.
In normal routing, yes. In VNet peering, no. The chain breaks. A can talk to B, B can talk to C, but A cannot reach C.
Why?
Because VNet peering only knows about the direct connection. It doesn't automatically route to the next hop.
So if I really need A to talk to C, what do I do?
You have to put a router like a firewall or a network virtual appliance and NVA inside network B to act as a bridge. But natively, the chain stops at one hop.
Got it. Now, speaking of chains and saving money, there was a term in the sources, gateway transit. This seemed to be linked to the hub and spoke model.
This is a huge money saver. Think about VPN gateways, the things that connect your cloud back to your on-premise office.
They're expensive.
They are expensive. They can cost hundreds of dollars a month per gateway.
And you don't want to buy one for every single VNet you own.
Exactly. So you build a hub VNet and you put the expensive gateway there. Then you peer all your little spoke VNets to the hub. By enabling gateway transit in the peering settings, those spokes can actually borrow the hub's gateway.
So they tunnel through the hub to get back to the office.
Right. You pay for the door once and let everyone use it. It simplifies management and cuts costs drastically.
Very efficient. Let's pivot to security. We've built the network, we've connected it, now we have to defend it. The source has introduced the Network Security Group, or NSG.
The bouncer of the cloud.
I like the bouncer analogy. But this bouncer seems to have a very specific clipboard.
It does. The NSG filters traffic based on what we call the 5-tuple hash.
That sounds complex.
It's simpler than it sounds. It just means the bouncer checks 5 things on every single packet: source IP, source port, destination IP, destination port, and the protocol. If those 5 things match a rule on the list, the traffic is handled.
And the list has a hierarchy, right? It's not random?
Correct. Every rule has a priority number between 100 and 4 years and 96. And the lower the number, the stronger the rule. Rule 100 beats Rule 200.
So if Rule 200 says, let everyone in, but Rule 100 says, block Bob, Bob is staying out.
Bob is going home. And there is a critical default rule at the very bottom of every NSG, priority 65,500. It says, deny all inbound.
The if you're not on the list, get lost rule.
Exactly. If you create an NSG and don't write any allow rules, absolutely nothing gets in. It fails, closed.
There's a debate in the sources about where to put these NSGs.
Mhm.
You can attach them to a subnet, or you can attach them directly to the network interface. The NIC of a specific VM is one better.
It's not about better, it's about sanity. You can put them on both, but that creates a troubleshooting nightmare.
Because the traffic has to pass both checks.
Yes, it's an intersection, not a union. If your subnet NSG allows web traffic, but the NIC NSG blocks it, the traffic is blocked.
I can just see an admin tearing their hair out. But the subnet allows it. Why isn't it working?
Exactly. That's why the general recommendation is to apply NSGs at the subnet level. Keep the rules at the neighborhood gate rather than trying to police every single front door. It's just much easier to visualize and audit.
Speaking of visualizing, let's talk about the pain of managing IP addresses in these rules. If I have 50 web servers, do I have to type 50 IP addresses into my allow rule?
In the old days, yes. And when you added server number 51, you had to go update the rule. It was tedious and incredibly error-prone. And that's why we have ASG's application security groups.
So how do those change the game?
ASGs are essentially tags. You create a tag called web servers. You stamp that tag on the NICs of your 50 VMs. Then in your NSG rule, instead of listing all the IPs, you just say destination web servers.
And if I add a new server?
You just tag it. The firewall updates automatically. It decouples your security policy from the specific IP addresses. It's a massive quality of life improvement for anyone managing a growing environment.
Okay, that handles application traffic.
Yeah.
But what about me? I'm the admin. I need to fix something on the server. I need RDP in for Windows or SSH for Linux. The old way was just opening port 3389 to the internet, wasn't it?
Which is like leaving your house key taped to the front door. I'm not kidding. There are bots that scan the entire internet for open RDP ports. If you open port 3389, you will see brute force login attempts within minutes. It's a massive attack surface.
So how do we manage servers without opening that door?
You use a secure tunnel. And in Azure, that's Azure Bastion.
Bastion. It sounds like a fortress.
It really acts like one. Bastion is a fully managed platform as a service solution. You deploy it into your VNet. When you need to connect to a VM, you just log into the Azure portal in your web browser. You click connect, and Bastion opens a session right there in your browser.
So the traffic is going over HTTPS, port 443.
Correct. Encrypted web traffic. The VM itself doesn't even need a public IP. It doesn't need open ports to the internet. The Bastion host acts as the middleman or the jump box, but you don't have to manage the OS of the jump box.
Now, the sources flagged a very specific gotcha when setting up Bastion. If you get the name wrong, it fails.
This is the most common deployment error. To use Bastion, you must create a specific subnet, and that subnet must be named case-sensitive.
A case-sensitive Azure Bastion subnet.
No spaces, no my Bastion.
No creativity allowed. Azure Bastion subnet. If you name it anything else, the service won't deploy. And it needs to be at least a 26 in size. Don't try to squeeze it into a tiny subnet.
That is a great tip for anyone listening who's about to click deploy and get a very frustrating error message.
It saves a lot of time.
All right, let's move to the final major piece of the puzzle. We've secured the VNet, but our apps don't live in a vacuum. They need to talk to Azure services, storage accounts, SQL databases, key vaults. By default, those services live on public endpoints, right?
They do. And that feels wrong when you've spent all this time building a private network. Why should your private VM go out to the public internet just to write a file to Azure Storage?
So how do we fix it? The sources offer two paths, service endpoints and private endpoints. They sound similar, but the architecture is totally different. Let's break them down. Service endpoints are the older method. Think of it as a secure route. You tell your VNet, hey, when you talk to storage, don't use the normal internet path. Use this direct tunnel on the Microsoft backbone.
But does the storage account still have a public IP?
Technically, yes. But with service endpoints, you can configure the storage firewall to say, only accept traffic from my specific subnet. So it's a public door, but the bouncer only lets your people in.
Okay. So what is the next level option?
Private endpoints, also known as private link. This actually brings the service into your VNet.
In the room.
In the room. When you set up a private endpoint for a storage account, Azure gives that storage account a private IP address from your VNet like 10.0.5.
So to my VM, the storage account just looks like another server on the local network.
Exactly. It is completely removed from the public internet. This is vital for data exfiltration protection. With private endpoints, the traffic never leaves your private boundary.
But there's always a but. The notes mentioned that private endpoints wreak havoc on DNS if you aren't careful.
It's always DNS. See, your application is still trying to talk to mystorage.blob.core.windows.net. Globally, that name points to a public IP.
but we want it to go to 10.0.5.
Right, so you have to override that DNS resolution. You need to set up a private DNS zone so that when your app asks, where is the storage, the network whispers back, it's at 10.10.0.5.
And if I miss that step,
Your fancy private endpoint exists, but your app just ignores it and tries to go out to the public internet. You have to sync the DNS.
that seems to be the theme here. Great power, but you have to configure the details, the subnet math, the NSG priorities, the DNS overrides.
That's the difference between a cloud environment that just works and one that is actually engineered. You are assembling these blocks, VNet, peering, NSG, Bastion, private link, to build a system that balances performance with security.
It's quite the ecosystem. And I think we've covered the core of what a network admin needs to know to survive.
We have. But before we go, I want to leave the listeners with one final thought. We've talked a lot about how Azure routes traffic automatically, local stays local, internet goes to internet, but sometimes you don't trust the autopilot.
What do you mean?
Sometimes security compliance requires you to force traffic through a specific firewall appliance, even if Azure knows a faster shortcut. You want to override the GPS.
Can you do that?
You can. It's called user-defined routes, or UDRs. You can literally rewrite the routing table of the cloud to force a next hop of your choosing. It gives you ultimate control, but be warned. If you get the routing table wrong, you can break connectivity for your entire network in a single click.
User-defined routes. Definitely a double-edged sword to explore for next time.
Indeed, it's the ultimate power move.
Thank you so much for breaking down the digital nervous system for us.
My pleasure.
And to you listening.
Yeah.
Check your subnets, watch out for those missing 5 IPs, and maybe double-check that your Bastion subnet is spelled correctly. We'll see you in the next deep dive.